Good morning, everyone. We are going to start now the physics class. In the last class, we had a discussion regarding the X-ray diffraction and what are the applications of X-ray diffraction. So today, in this class, we are going to start up the planes and the Miller indices, how the planes are formed with the imaginary lattice points, and how these planes are related to Miller indices that we are going to discuss in today's class. So we'll just start with the planes in the lattices, right? So we go to the next slide, that is planes in the lattices and how they are related to Miller indices. So now this is an important concept, very important concept. Why? Because these concept will give us the clear relationship between the diffraction of X-rays by the crystal lattices in the presence of planes, and we call that particular planes as the families of the planes and the given imaginary points. That imaginary points in the space is said to be crystal lattice, and each plane is constructed. So how this plane is constructed? So this plane is constructed by means of three imaginary points, three different lattice points, which have been what you can say brought together. So since the lattice points are in periodic nature, right, in a sequential order, so we'll have a series of planes which are parallel to these lattice points. So the easiest way to describe the orientation of these planes with respect to the Miller indices HKL, in which the plane makes the intercepts with the unit cell. And these intercepts, you already know that the intercept form is nothing but x by a plus y by b plus c z by c is equal to 1, right? If I talk about three dimension. So therefore, here we are just writing this intercept with respect to the unit cell as a by h, comma b by k, and c by l. Thus, the Miller index indicates the reciprocal of the intercept. So whatever the intercept is there, so that reciprocal is represented by the Miller indices. So for your convenience, what I'm doing here is that, so you can just see the diagram, right? Each plane here. When I talk about a plane, so this plane, you can just see this imaginary points, right? One, two, three. We just now we had very clear what you can say uh, information regarding how these planes are formed. So these planes have been formed by using the imaginary points, that is the crystal point, crystal lattices. We can say that lattices are nothing but, so this is one point, this is another point, and this is third point, and so on. By which I'm just you can just see the diagram, and in that diagram it has been marked with some color, right? By using this pen. In a sense, this is for your convenience, for your understanding purpose. So I'm just marking it as a, see, green color. You can, everybody can see this. So these particular points, when they are joined together, any 3 point, these 3 points are nothing but HKL plane. We call that as HKL. How the planes can be designated with respect to the imaginary points has been shown in the diagram. You can just see the diagram, and these particular concept has been taken into consideration to understand the distribution of atoms, how these atoms are distributed, how the this can be distributed in the solid. So that information will get if you just imagine that the uh, atoms are nothing but how the atoms are arranged, right, in a sequential order. We just consider that, let us imagine that the atoms in a solid is considered to be in a sequential order. So in ideal way, I'm talking about in ideal way. So in the ideal way, these atoms are what you can say are arranged in a sequential order. So now why we need to understand this diffraction of X-rays, we had already discussed in our last class. Now, how this diffraction is taking place, where the X-rays are made to incident, that particular thing I have been explaining you. In the last class also I had explained you. In this class, it has been shown that how the planes are formed. You can just see these planes in the figure A, how these planes are formed, right? With respect to different orientation. You can just see this. This figure A, figure B, and figure C represent how the planes are formed with different orientation. So this is about the formation of the planes in the lattices. And then we go to the next slide. So in the next slide, we can now we had previously we had an information regarding the lattice distribution and whatever the thing that we have just gone for. This is what two dimension. See, whenever I talk about the for lattice points. So our neck die can see only two dimension. And here, the regarding the Miller indices, one everybody should keep in mind that the if the plane is not intersecting any axis, right? So here you can just see that by means of this two-dimension plane, I want to show you that there is two axes, right? So x-axis and y-axis. So if a plane does not intersect an axis, so if it is not intersecting an axis, what is the meaning of intersecting? You can just see this particular point here. So this point, uh, this is the line, and this line or this particular line segment is intersecting at this particular point. So if a plane does not intersect an axis, then the intercept of that particular axis is taken as infinity. And definitely 1 by infinity, that is called reciprocal of the 1 by infinity, will give us the value 0. And if this reciprocal of the intercept is a fraction, so let us consider the reciprocal. You got some a by b in the particular fashion. So you have to multiply each of these HKL values by the lowest common denominator. That lowest common denominator you obtain by taking the LCM such that they should become an integers. So this is the important, very important aspect. Now, in order to find, whenever you are finding out the Miller indices, you need to understand this that if a plane is not intersecting an axis, then the intercept of that particular what you can say axis will be taken as infinity, and definitely the reciprocal is taken as 0. And if the reciprocal of the intercept is any fraction, then you have to multiply that fraction value with the HKL values, and by the lowest common denominator means you have to take an LCM. So why we are taking this? We want to become make that particular value as an integer. So you will get a very simple value in the simplified form. That is the reason that we are just multiplying with a what you can say the HKL values is multiplied with the lowest common denominator. Now we just go to the next one. So hope that I have make you understand what is actually the plane and how this plane is formed by considering the three imaginary point, or we can say that three imaginary points are nothing but the crystal points. And when these planes have been formed, and if they are interacting with the electrons in the crystal, if the see if they interact with the electrons in the crystal, that what is the meaning of that? It means that any incident X-ray will get scattered, and these X-rays are scattered. How they are scattering? I will show you the diagram that when the X-rays are scattering, they are how this particular X-rays are getting scattered. So if these, you can just see this first diagram, right? Everybody, please have a glance of this particular first figure such that you can easily understand what is happening when I incident the X-rays. So that X-ray when incident on the plane, that you can just see this particular point here, this points, right? These are the what you can say the distribution of crystal lattices. So when I incident the X-ray, it is getting scattered, and here, so some of the X-ray will go to the next second crystal plane and they get scattered. So what is happening when I compare with the first plane with respect to the first X-ray with respect to the second X-ray, you can say that they are in phase. then only if they are in phase, then only the interference pattern will is constructive, and this will give you us the different reflections. And by using the Bragg's law to interpret the diffraction pattern with respect to the interplanar spacing. So what is that interplanar spacing? I've just shown you in the previous class also the distance between these consecutive. So you can say DHKL represent the interplanar spacing, and how this interplanar spacing is related, we have shown with this dotted lines, right? So when you just incident the ray here, the ray has been incident, it has been shown by the red color, and this is the second X-ray which has been incident in the second crystal plane, and this is the third, and so on. This process will be in a sequential order. So this particular value, now you can just we just take the consideration of angle here. These X-ray is making with this particular crystal plane an angle theta. When it is getting a incident and then it is coming back, the ray A, the ray B is coming back. So it is this plane with respect to the other plane is making definitely the angle 2 theta. So in order to explain this value very clearly, you can just see the third diagram. So whenever the see, whenever I incident the X-ray, so it getting scattered. So when it is getting scattered, it is making the angle, this angle you can see, this is called diffracted angle, or we can say that is the diffraction angle. Here the line segment indicates the orientation of the surface of the crystal plane. So yeah, now I think that you had some idea regarding how these planes are being formed, and the distance between the two consecutive planes is given by DHKL, which indicates that the interplanar spacing between any two consecutive crystal planes. So I think that you got the exact concept of the planes. Here I am very much interested in order to tell you about the exact nature of the plane and how these planes are formed. Now we'll go to the next slide, so you can easily, and this here, the diffraction angle is generally here is labeled as 2 theta because of the geometrical relationship which has been shown in the left diagram we have just now you have shown you. So now we just give our what you can say and important to the next topic. We give our concentration to the next topic. I just now explained you regarding the DHKL plane. So that DHKL plane is nothing but it is the interplanar spacing, or you can say the interplanar distance. So what is actually the definition of the interplanar spacing or interplanar distance? These interplanar distance is actually defined as the distance from the origin of the unit cell. So if someone asks you regarding the definition of interplanar spacing, so definitely what will be the interplanar spacing or the distance? These interplanar spacing or distance is actually defined to be the distance from the origin of the unit cell to the HKL plane nearest the origin, and this origin is exactly along the normal to the plane, and which will that is right, that is nothing but the perpendicular distance from the origin to the next consecutive plane. So if I take a plane which is what you can say is passing through the origin of the unit cell. So what it means that whenever a plane is passing through the what you can say origin of the plane, the next plane will pass through a distance equidistant, that equal distance with respect to the another plane is nothing but we'll call such distance as the interplanar distance. And how this plane is passing? So that is actually the perpendicular distance from the origin, that has been taken as the perpendicular distance which is passing through the origin. So now, so that is actually the definition of interplanar distance. And how we can evaluate mathematically this interplanar distance? See, in physics, particularly when you talk about any statement, that statement should be verified mathematically, and that mathematics can be easily done by considering the what you can say the figure. The next figure I will show you how we can calculate the interplanar distance of the two consecutive plane of the given unit cell. So now we'll just move to the next slide. In the next slide I will make you understand how we can calculate geometrically the interplanar spacing. So for that instant you can just see the figure. I'll see the plane which is passing through the this particular figure. You can see the figure where the origin is taken at the reference point from which the plane is passing through, and the another plane which is passing through the from the origin. So that particular plane is I'm considering that particular point where this plane is formed, and that is considered to be the point P. So from 0 to P, if I get that distance value, that distance will give me the information about the interplanar spacing of any crystal system. See, you already know that we are actually having 7 crystal system. Now in that crystal system, definitely each crystal system will have some crystal planes. So in generally, how we can locate the interplanar spacing of any crystal system, that actually we are trying to derive here. So first of all, the geometrical assumption what we have to make is the 3 axes. You can just see OX, OY, and OZ, and the perpendicular distance from O to P is nothing but small d, and they are, see, you already know these angles are nothing but crystallographic, right, axes, right? Or you can say this is interfacial angles. OX is the crystallographic axis along x-axis, OY is the crystallographic axis along y. So and OZ is the crystallographic axis along z. And definitely OX is making an angle alpha, OY is making an angle beta with respect to the perpendicular distance which has been taken from the origin, and here OC is making the angle with respect to the OP, that is called gamma, which has been shown with some what you can say square brackets here. So here this angle is alpha and this is beta. So you can just see the angle made with respect to the perpendicular distance, that is OP. That is very important. So that is the angle is alpha, here beta, and here that is called gamma. So now this particular aspect here, you can just see that it can be more clearly. I will show you with the this particular with the pencil. So this angle, you can just see this. I'm talking about this particular angle here. This angle is alpha, right? This angle is alpha. Here, this angle is called alpha. Uh, yeah, you can very understand here. This is gamma. This angle is gamma. I'm talking about this angle, and this is beta with respect to this y-axis. So you can just see that how these angles have been formed with respect to the common origin, and each angle is incomparable with the perpendicular distance OP. Now you can just see that this particular and how the angles are formed. So now what I'm doing here is that now I think that you got an exact idea. So now we just go to our what you can say this one. So now we just understood only the diagram. Now we'll go to the same slide. Right, now see here. So this is for the understanding purpose how these geometrical planes have been formed. You can just see this line segment. It is in you can see it's the form of a what you can say right angle triangle. You can see here ABC is a right angle triangle, and this particular dotted lines is another plane, right? So we are just and the plane which is passing to the origin. So whatever the thing that I'm trying to tell, this is a three-dimensional geometrical figure, and these three-dimensional geometrical figure has been shown to you in 2 dimension. So now how this is about the figure. Now I think you got some idea regarding the figure. Now let us consider these three mutually perpendicular coordinate axes. How you are going to write this? By seeing the figure, you should able to write the some sentences regarding whenever someone asks you in the examination, derive the relationship between interplanet spacing uh, and the Miller indices, then definitely you need to write some sentences by seeing the diagram, geometrical diagram. So let us consider these three mutually orthogonal or perpendicular axes OX, OY, and OZ, and assume that a plane HKL is parallel to the plane which is passing through the origin. See, this is alpha, this is beta, and the third one is your gamma. So here you can just see that what you can say, we need to know the exact distance between the plane which is passing through the origin. So here let us consider three mutually perpendicular coordinate axes OX, OY, and OZ, and assume that the plane HKL is parallel to the plane which is passing through the origin. And when I say passing through the origin, definitely it will make some intercept along the OX. So it is making some intercept along OX, and that intercept is given by A by H, and that you can just see this. Therefore, here you are seeing this, right? OA is equal to A by H, and OB is equal to B by K, and OC is equal. We can see OA is A by H, OB is B by K, and OC is C by L. Now OP is what you already know, that is DHKL, and the interplanar spacing, which is normal to the plane which has been drawn from the origin and making the angle alpha, beta, gamma. So now you can just see there is a right angle triangle OPA. When you see this right angle triangle OPA, you can just see here OPA. This is one right angle triangle. When I take this OPA, see what is my aim? I want to calculate the value of OP. That value of AP you already know, that is DHKL. So what trigonometric ratio that I have to take here, that is called, we get cos alpha. You can see that square bracket, that is actually alpha. Here I have to write this as alpha. So cos alpha is equal to adjacent by hypotenuse. What is the ratio? So any right angle triangle. So what is OP? OP is your adjacent side, right? And I'm talking about OPA. So where is the angle form? So angle is alpha. So now I can just you can know that OP by OA, that is adjacent by hypotenuse. So what is that hypotenuse value? So hypotenuse value is nothing but it is OA. So OA is OP by OA will give me the value of cos alpha. So cos alpha is equal to DHKL. You can just see this. So OP is DHKL, OA is equal to A by H. You can just see here, this is the intercept along the crystallographic axis X. So instead of OA, what I can write here? A by H. Now, similarly, just I will go for the right angle triangle. Here I'm talking about this particular right angle triangle. Here this O, you can see this OPB. This is right. This is one right angle triangle, another right angle triangle. You can see. So this is three-dimensional. Actually, this is three-dimensional figure. So this is nothing but we call OPB is nothing but here. See, this is your beta, the cos beta. So cos beta is equal to, again, adjacent by hypotenuse. So here OB is the longest side, and that longest side is nothing but you can just see, that is B by K. So cos beta is equal to OP by OB. That is called OP. You already know DHKL by B by K. Now I will go for the next right angle triangle. So this is next right angle triangle. What is that one? OP. See here, you'll find that this is another right angle triangle, OPC. So OPC is nothing but this is what gamma. So cos gamma is equal to OP by OC, that is DHKL by C by L. You can see I'm talking about OC, that is C by L. So now I got these three right angle triangles, and I got the trigonometric ratio cos alpha, cos beta, and cos gamma. So now what I'm trying to write, this is equation number one, this is equation number two, and this is equation number three. Cos gamma is equation number three. So you already know that using the directional cosines you studied in the planes, right? So cos square alpha plus cos square beta plus cos square gamma. You see, this is the directional cosine condition. This is called cos square alpha plus cos square beta plus cos square gamma is nothing but it is 1. So substituting, I'm just substituting this cos alpha value, cos alpha value, cos beta value, you already know from equation 1 and 2 and 3, and just substituting it. So how, what I will get? D square HKL by H square, you can just see here, D square HKL, D square HKL, uh, D square HKL, H square by A square plus K square by B square plus L square by C square, you get that is equal to 1. So you just simplify it, you'll get DHKL. We want DHKL value, right? So when you simplify it, the next what I will get? DHKL is equal to 1 by under root of H square by A square plus K square by B square plus L square by C square. Now this is the interplanar spacing derivation for finding out the interplanar spacing of any crystal system. So I think that you had a very clear idea. You had a very clear idea how we can find out the interplanar spacing. Right? So now I think that everybody is at least you got some concept of interplanar spacing. Now, what is actually X-ray diffraction? Now we are going to see a video. Now, what is actually X-ray diffraction and how this X-ray diffraction is important for the what you can say how this X-ray diffraction is important in our daily life. Right? You can just please see the video regarding the X-ray diffraction. Okay. I will start the video now.
What is X-ray diffraction, and what is it used for? In an X-ray diffraction experiment, a sample is placed into the center of an instrument and illuminated with a beam of X-rays. The X-ray tube and detector move in a synchronized motion. The signal coming from the sample is recorded and graphed, where peaks are observed related to the atomic structure of the sample. Most materials are made up of many small crystals, like sand on a beach. Each of these crystals is composed of a regular arrangement of atoms, and each atom is composed of a nucleus surrounded by a cloud of electrons. It's at this scale that the story of X-ray diffraction begins. X-rays are high-energy light with a repeating period called the wavelength. Since the wavelength of an X-ray is similar to the distance between atoms in a crystal, a special interference effect called diffraction can be used to measure the distance between the atoms. Interference occurs when X-rays interact with each other. If the waves are in alignment, the signal is amplified. This is called constructive interference. If the waves are out of alignment, the signal is destroyed. This is called destructive interference. When an X-ray encounters an atom, its energy is absorbed by the electrons. Electrons occupy special energy states around an atom. Since this is not enough energy for the electron to be released, the energy must be re-emitted in the form of a new X-ray with the same energy as the original. This process is called elastic scattering. In a crystal, the repeating arrangement of atoms form distinct planes separated by well-defined distances. When the atomic planes are exposed to an X-ray beam, X-rays are scattered by the regularly spaced atoms. Strong amplification of the emitted signal occurs at very specific angles, where the scattered waves constructively interfere. This effect is called diffraction. The angle between the incident and the scattered beam is called 2 theta. In order for constructive interference to occur, the scattered waves must be in alignment, meaning that the second wave must travel a whole number of wavelengths. In this case, 1/2 of a wavelength is traveled on the incident side, and 1/2 on the scattered side, yielding 1 additional wavelength. In the case of the next X-ray, 1 wavelength is traveled on both the incident and the scattered side, resulting in 2 wavelengths. This reinforcement occurs throughout the crystal. The exact angle at which diffraction occurs can be determined from the red triangle. The angle at the top is theta, half the angle between the incident and scattered beams. The long side is the distance between the atomic planes, and the short side we know is 1/2 of a wavelength. The relationship between the diffraction angle and the spacing between the atoms can be determined by applying the sine function. Rearranging this equation yields an equation commonly known as Bragg's law, named after Sir William Henry and William Lawrence Bragg, the father-son team who won the Nobel Prize in 1915 for their work analyzing crystal structures with X-ray diffraction. This technique of X-ray diffraction is used today for a wide variety of materials, ranging from single crystal epitaxial thin films to polycrystalline mixtures of powders, and even randomly oriented amorphous materials. X-ray diffraction helps scientists to develop new pharmaceuticals, classify rock formations based on their mineral components, and understand how the arrangement of atoms affects the behavior of energy storage materials. As scientists push their ability to engineer materials on the atomic level, X-ray diffraction becomes an increasingly important tool in their toolbox. Advances in equipment design have made X-ray diffraction easier to use and more powerful than ever.
So now you have just seen the video, and in that video we had explained you what is X-ray diffraction and how this X-ray diffraction is used to a layman, right? So with this explanation, we just come to the end of our class, and in the next class we just have a revision. See, what has happened is that due to some technical issue, one of my class have been having some technical issue. That is the reason that some sound was there in the background. So that particular class, I will just share you that revision class. So in the next class will be the revision class. So that particular class will be the in compensation of the class 4 of physics. So the next class will be completely revision what we have completed till now from starting, right? So thank you everyone for your what you can say patience. So I think that you got some concept, and definitely you have understand the topic. So thank you everyone.